Continuing the discussion on relations, we've been talking about certain type of relations called equivalence relations. So a relation, twiddle, on the set A is called an equivalence relation when it satisfies the following three properties. Reflexive, every x is related to itself. Symmetric, the order of the relationship doesn't matter. When you say x is related to y, it's the same as saying y is related to x. That's not always true, but for equivalence relations, that's one of the requirements. And then transitivity, when x is related to y and y is related to z, then x is related to z. All right. And we looked at several equivalence relations. Consider a partition of sets of a set A. So partition is when you express A as a disjoint union of some subsets. And two elements of A are related when they're in the same block of that subset. That was an equivalence relation. And second equivalence relation was on the set of integers, a very important one, gets used a lot. Given a positive integer n, at least two usually, don't usually take one. Define a relation on the set of integers as follows. You say that x is related to y when n divides x minus y. That is, y minus x is a multiple of n. That's an equivalence relation. It's called equivalence modulo n. And you have to show that it satisfies the three properties of equivalence relations. And then this one here, given a finite set A, okay, we're not going to define a relation on A, we're going to define a relation on the power set of A, which is a set of subsets of A by x is related to y. Two subsets of A are related when their symmetric difference has even order. And, we showed it satisfies the same three properties, although transitivity definitely took a little bit more doing than most things that we've done so far. Okay. So given an equivalence relation, relation twiddle on a set A and x in A, define the equivalence class of x as, so it's bracket x equal to the set of all y in A such that y is related to x. Okay?
So in other words, a element's equivalence class is just how many things it's related to in the set?
Sorry?
So in other words, an element's equivalence class is just the amount of other elements it is related to in the set?
No, not the amount of, the set of. The set of everything it's related to. Not the order, not this. Bracket.
Okay.
Yeah. Mm-hmm. It's
the actual elements then.
Yeah, okay. So,
Okay.
Now, before, so what I'd like to do is take a look at equivalence classes of equivalence relations, but before that, there's an especially important theorem that we need to look at. If X, well, so if twiddle is an equivalence relation, well, let me do it this way. Let twiddle be an equivalence relation on a set A, and let X and Y be elements of A. Then, the equivalence class of X equals the equivalence class of Y. In other words, a set of things related to X is equal to the set of things related to Y if and only if X intersects Y is not equal to the empty set. Well, let's say it this way. The equivalence class of X is not the same as the equivalence class of Y if and only if they're disjoint. Which is equivalent to, we'll say it both ways, I guess, which is equivalent to the equivalence class of X is equal to the equivalence class of Y if and only if they're not disjoint. I thought I said twiddle. Oh, let twiddle be. Yeah, how about that? All right. So two equivalence classes are either the same or they're disjoint. They don't overlap. There's never an overlap between equivalence classes. Okay? No intersection. I mean, if there is an intersection at all, then if there is an intersection at all, then they're actually the same. So equivalence classes are totally the same or totally different. All right, proof. So this is an if and only if proof. So before we do that, let us write a note. To prove P if and only if Q, okay, to prove P and if and only if Q, we must prove what?
That both P implies Q and Q implies P.
And to prove P implies Q, there are three strategies, three basic strategies. I keep saying the same thing over and over. Why do I do that? Because I'm old and getting senile, or why do I keep saying the same thing over and over again?
Probably because you're old and getting senile.
Yeah, that's probably it. But there's another reason that goes along with it.
Because these things are super important.
Yeah, it's super important. You got to know it. Okay, super duper duper ooper snooper important. You have to know it. So please, you guys. I mean, these little things that I keep repeating. These are basic elements of what we're learning here. So there's direct proof. Assume P, show Q. There's contrapositive. Assume Q is false. Show P is false. And then contradiction. Assume assume that P and Q is false. When is an implication false?
When P is true and Q is false.
Assume P and Q not, find R and R not. Now, of course, R and R not is always, contradictory, right? It's always false, but you're going to find R that's true and R not that's also true, but, that can't happen. Right? So, all right. So lots of different implications floating around in here. This is a multi-part proof, okay? So, first we got to show P implies Q and Q implies P. So, let's take the first statement, okay? That X. No, let's do this. Let's assume that the equivalence class of X not equal to Y if and only if. No, I thought one direction is definitely, both directions were non-trivial. Well, the first direction is trivial, so I'm going to write down both instead of writing just P implies Q and Q implies P, or just writing an arrow. I'm going to actually, I'm going to actually, write down the implication. So first, let's show X equals the equivalence class of X equal the equivalence class of Y implies X equivalence class of X intersect the equivalence class of Y is non-empty. Okay, so the first part of the proof, oops, go back to black. So equivalence class of X equal to the equivalence class of Y implies X intersect Y is not the empty set. All right. So to do that, what's the first? So this is an implication statement. What's the first sentence of that implication statement supposed to be? Or the first sentence of the proof of this implication statement. Say, let's do a direct proof.
Assume the class of X equals the class of Y.
I'm sort of, repeating myself, and, I'm kind of expecting a resounding, thundering noise from the whole class to say in unison, assume that this X is equal to bracket X is equal to bracket Y, but I'm kind of not getting, I'm always kind of getting one or two of the same people saying that, which is fine because I know that they're getting it, but, I don't know that you guys are getting it.
Little does everyone know, but the only question on the final exam is how do you prove an implication statement?
Right, no.
And there's 3 different ways.
Don't say that. That's, yeah. There are certain jokes you can tell in a class, that kind of thing you can't, because sometimes people, oh, let me write that down, and like, but you said this. So assume that bracket X is equal to bracket Y. Okay, does that mean that their intersection is non-empty? Oh, not equal to the empty set. Does that mean their intersection is non-empty? If two sets are equal, does that mean their intersection is non-empty? I mean, your intuition would be telling you, well, yeah, sure, of course, except in one case. There's one case where it doesn't imply that.
If the two sets that are equal are empty themselves.
If the two sets are empty themselves. As long as the two sets are not themselves empty, then yeah, of course. Right? So this obviously implies that x intersect y is non-empty as long as, except when, well, as long as is not equal to the empty set. You know, but bracket x is not equal to the empty set because what in particular is related to x? There's always guaranteed to be one thing related to x in an equivalence relation.
X itself.
X itself. In order to show a set is non-empty, all you got to do is show that there's one thing in there. Yeah? In order to show a set is non-empty, all you got to show is that there's one thing in that set. As a matter of fact, that's the best you can do in this case because that may be it. The equivalence class of x may just be x itself. I mean, there are various equivalence relations where you know, that is true. Okay, so you know, again, in order to show that a set is non-empty, just got to show that there's one thing in there, right? I mean, it's like when you're talking to people, right? You know, and people say, well, you know, everybody likes chocolate. Is that true?
Sadly, no.
Sadly, no. I mean, you know, you probably most people do. You know, I mean, that's kind of like, you know, when you're talking to people who say, you know, well, people like chocolate. I mean, no, you know, there are a few people out there that actually don't. Okay, probably they're somewhat rare. I think most people do like it. Right. So, you know, and then, you know, that person may ask, well, who? Well, my friend over there, he doesn't like chocolate. Really, truly, he doesn't like it. You know, and that's all you got to do. That's all you have to do is just show that there's one person that, you know. Again, to disprove the universal statement saying nothing is in X, for everything that thing is not in X, all you have to do is show there's one thing in X, just one. Okay, so that part of the proof is actually not quite so difficult. Okay, it just has one little sticking point to it. All right, what's the next thing we have to prove? So this implication is done. What next? What would be the next implication we have to prove for this if and only if statement? So I mean, these statements are equivalent. So you know, I'm doing the bottom one actually.
The other way around, that the intersection of x bracket and y bracket equaling not equaling nothing implies that x bracket equals y bracket.
Yeah, that they're the same. So the other way around is bracket x intersect bracket y not equal to the empty set implies that bracket x is equal to bracket y. Okay, so assume what? First sentence of this proof. Come on, everybody, in unison. Let me know that you understand this, please.
Assume the class of x intersect with the class of y does not equal the empty set.
Okay. Thank you. However, this person has who was it who said that? Was it Matthew or Evan?
Which person?
Yeah, I mean, this person. I'm sorry, I can't match faces to voices, unfortunately.
This is Kai Terrell.
Kyle. Okay, that's great. Kyle has said that many times. This sort of thing. So, could we please all in unison say it? 1, 2, 3. If you don't want to turn on your mic, don't turn on your mic. Okay, look at this right here, and tell me the first sentence of the proof. Okay. Say it to yourself without your mic on. 1, 2, 3. Okay. I'll assume you all said it. I mean, it's like a conductor, in front of the concert band or the orchestra or something. You hold up your baton. I don't know if any of you were in band or whatnot in high school. And you go 4, 3, 2, 1, and then nobody plays. Right? It's kind of it's disappointing. All right, so assume that bracket x intersect bracket y is not equal to the empty set. Okay, specifically, what does that mean? Specifically, what does that mean?
They share something in common?
Sure, what do you want to call it? You can't necessarily use x or y because it may not be that element. You actually have to show it.
That there exists an element A.
Oh, A, sure.
A
okay.
is in both X
Right, you
and Y.
got to give that thing a name. There's something in common. Say that Z is an element of X intersect Y. All right. So now, in order to show that, set X equals set Y, we must show what? So proofs within
that set X is a subset of set Y and vice versa.
Right, that X is a subset of Y and bracket Y is a subset of bracket X. Okay. However, they're the same proof. They're just switching the roles of X and Y. Okay. Of the two statements. Are identical aside from switching the roles of X and Y. It's the same proof. I mean, there's nothing particularly special about X as opposed to Y in this proof. I mean, you might not have known that ahead of time, but I'll let you say, I'll let you know ahead of time here that this is going to be the case. All right, so we need to show that. So now we need to show. So let's just show that bracket X is a subset of bracket Y, and that'll be enough. So how do we show bracket X is a subset of bracket Y?
That for any arbitrary element in bracket X, that element is also in bracket Y.
Right. So what element would you like to work with?
A.
Yeah, great. So let's just show that X, bracket X is a subset of bracket Y. Let A be an element of bracket X. All right. Now we gotta look at Z because Z is in bracket X. Because Z is in, well, first of all, before that, because A is in bracket X, it means what? What does it mean?
It's in bracket Y also.
Well, not necessarily, because their intersection is empty. We want to show that they're equal, right? So we got to show that A is in bracket Y. But what does it mean by definition? That
That A is related to X.
right. The bracket X is the set of all Y, such that Y is related to X. So it just means that A is related to X. And because it's an equivalence relation, you also get what? Equivalence relations are symmetric, right? So A is related to X, and symmetry.
So A is also related to Z.
The symmetry. A is related to X, and
X is related to A.
X is related to A, right? Yeah. Okay. Because Z is an element of bracket X, we get that what?
Z and A are related.
Yeah, we similarly get no, not yet. By definition, because Z is in bracket X, what do we get?
Oh, Z and X are related.
Z and X are related, right? Z is related to X, and X is related to Z by symmetry. Symmetry. Now, transitivity implies that what? So I got A is related to X, and X is related to Z.
A is related to Z.
Yeah, A is related to Z, and Z is related to A. Okay. Now, because Z is also where? It's in bracket X, but it's also in it's in the intersection of bracket X and bracket Y, right? So Z is not only in bracket X, it's also in what?
Bracket Y, which makes it related to Y.
Yeah. So because Z is an element of bracket Y as well, right? Z is related to Y, and Y is related to Z. Therefore, by transitivity, what? Y and A.
Z is related to, sorry, not Z, Y is related to
Y
X
is related
and
to. Oh, we're looking for A in
and
this
Y
case.
and A.
Y is related to A, and A is related to Y. So A is also in what set?
Bracket Y.
Bracket Y.
Is it necessary to write both Y related to A and A related to Y? That feels more.
Yeah,
extra-worded.
because to use transitivity, right? Transitivity is that, let's see, P is related to Q and Q is related to R, implies P is related to R. So the ordering matters there. Right? It's like this, right? Like when P, for integers, P is less than or equal to Q, and Q is less than or equal to R, implies P is less than or equal to R.
Okay.
Right?
I just feel like since transitivity is only used in equivalent relations, which
Well, no,
always means
this
related
is
both ways.
yeah. On the set of integers, less than or equal to is not an equivalence relation because it's not symmetric.
Yes.
So the ordering of the relation matters, but with equivalence relations, it doesn't matter. So I'm just sort of emphasizing that point.
Okay.
Okay. If you wrote in the proof just one direction, I mean, if you wrote in the proof just, A is related to X, and then, Z is related to X, therefore X is related to Z, I'd be totally fine with that. Without taking into account any of the ordering, right? If you just wrote A is related to X and Z is related to X, therefore Z is related to A, right? But that needs symmetry here, right? A related to X and Z related to X does not give you Z is related to A by transitivity. Z related to X and X related to A gives you Z is related to A by transitivity. But if you left that out in this proof, I'd be totally okay with it, because I would think to myself, my assumption is that you know what you're saying, right? My assumption is that you know what you're saying. So I would assume, okay, he's just assuming symmetry, at every step and not bothering to write it down. If you did write it down, I'd be like, okay, that's fine. He's writing it down.
Okay, good to know. Thanks.
Yeah. So my assumption is that you know what you're writing. When you write, you know what you're writing. Unless there's some reason for me to believe otherwise. I remember when I was in graduate school, I had a professor, and like towards the end, when I was just about to finish and stuff like that, like I was asking about, because I took an oral exam with him one time, and oral exams are tough. I mean, you get up in front of a committee and they're giving you an oral exam. It's intimidating, because you can mess up and it's an exam situation. So, I said, how do you give an oral exam? How do you know when somebody is? How do you know when somebody? What did I say exactly? Yeah, how do you know when a proof is enough? Like, I mean, if I just say this is true, when do you take it to be true? And he said, well, as long as you say it confidently enough. Because, like, if you say it confidently enough, it means that you really knew that to be the case. Right? So, anyway, so let's take a look at that again. So that's it. That's the end of the proof right there. Because we did what we wanted to do. So I should write as required. Right. The goal was to show that bracket X is a subset of bracket Y. So we pick A in bracket X, and we just show that A is in bracket Y. So that's what we want to do. For every element in bracket X, that element is in bracket Y. So bracket X is a subset of bracket Y, and then the proof that bracket Y is a subset of bracket X is exactly the same, except you swap out X's for Y's. Let's look at it again. So we're trying to show that bracket X intersect bracket Y being non-empty implies they're actually the same. Okay, it's an implication statement, so we start with the sentence for direct proof. We start with the sentence. Assume that bracket X is not equal to bracket Y. Bracket X intersect bracket Y is not equal to the empty set. That is, there's some element Z in bracket X intersect bracket Y. You can't assume that element is anything in particular. Right? When there's an existence statement, there's nothing that you can really assume about that element that exists. Okay, you can try proving stuff about it, right? But I mean, there's nothing off the top that you can really assume. So in order to prove that bracket X is equal to bracket Y, we have to show that bracket X is a subset of bracket Y and bracket Y is a subset of bracket X, but those are the same proofs. So we'll just show that bracket X is a subset of bracket Y. In order to show this, you got to take an element of the left-hand set and show that it's in the right-hand set. Okay, so now the proof begins, the real part of the proof. Let A be in bracket X. By definition, that means A is related to X, and by symmetry, it means X is related to A. Now, that element z was in the intersection of bracket x and bracket y. Right, so say that z is in bracket x intersect bracket y, that is, right, z is an element of bracket x and z is an element of bracket y. Z is an element of bracket x and z is an element of bracket y. Because z is in bracket x, we similarly get that z is related to x and x is related to z. And now by transitivity, z related to x and x related to a gives us that z is related to a. And then by symmetry, a is related to z. Right? So you could use transitivity here. Whoops. X is related to z and a is related to x, so a is related to z. And by symmetry, z is related to a. Whatever suits you in that case. Now, that z was in the intersection of bracket x and bracket y. That is, z is in bracket x and z is in bracket y. So z is in bracket y, which means z is related to y and y is related to z. So now by transitivity, right, z is related to y, or no, the other way around. Y is related to z and z is related to a. Right? Y is related to z and z is related to a, therefore y is related to a and a is related to z. Or a is related to y. Which means, by definition, a is in bracket y. And that's what we wanted to show, and so it's a done deal. So equivalence relations give you equivalence classes, and equivalence classes do what? Right? Equivalence classes are either the same or disjoint. Either the same or disjoint, and never both. What does that mean? What do equivalence classes do to the set A? Starts with P. Equivalence classes do what to the set A? Starts with P. The word is P. The word starts with P that I'm looking for. It's a word we've used. Equivalence classes are disjoint. Each equivalence class is disjoint from the other one. And if ever, you thought they weren't disjoint, well, that means they actually were the same. So the equivalence classes do what to the set A? They what's the word with P?
It's that like container splitting one we were talking about earlier. I can't remember the word. Partition.
Partition. They partition the set A. So that partition equivalence relation is actually every equivalence relation. Every equivalence relation is just a partitioning of the set.
I have a question.
Yeah.
For the equivalence classes, is that only for equivalent relations? Like,
oh yeah, just equivalence relations, not other ones. No.
Okay.
Yeah. Oh yeah, that's
I missed that at first.
Totally just
no.
Just equivalence relations. There's other. I'm going to go over another relation after this. We're going to go over what's called the partially ordered sets, which is another type of relation which has nothing to do with equivalence relations.
Okay. And
they're totally not equivalence. There's no equivalence classes, nothing like that.
Okay. Thanks.
Okay. Yeah. So given an equivalence relation, twiddle on a set A. Okay, the equivalence classes partition A into disjoint subsets, where right? Bracket x is equal to bracket y if and only if, right, x is related to y. So that partitioning equivalence relation is actually every equivalence relation. Partitioning equivalence relation. In example, I guess we got to give it an example A, or example P, I guess. Example P. P above is actually every equivalence relation. So equivalence relations can be described, using the partition or using other descriptive type language. So let's try to find the partitioning of these other two equivalence relation examples. Given by equivalence relations given by the equivalence relations. And well, I guess I got to give those an example. So there's a modular, and we'll call it S for symmetric difference. So this is example S. This was example M. For modular arithmetic. So let's talk about example S first. Oh no, let's do example M. So remember, for n in Z plus, we have the relation, equivalence relation, we have the equivalence relation on Z called equivalence modulo n, which is defined by, so I'm not going to use the twiddle symbol anymore because there's actually a common notation, and it's this. X is equivalent to y, and then you just write mod n, or you skip the mod n. So this is used for equivalence modulo n, or like this. X is equivalent to y mod n when n divides Well, when x minus y is a multiple of n. So x is equivalent to y mod n when x minus y is a multiple of n. All right. In order to really sort of get our hands on what the equivalence classes are, well, I'll tell you what. Let me show you the equivalence classes, and then we'll note that yes, indeed, those are the equivalence classes. Okay, well, they are as follows. You have bracket 0. So when is, so 0 is an integer, so it's got to have its own equivalence class. What's its equivalence class going to be? When is, 0 minus y a multiple of n? When is 0 minus y a multiple of n?
When y is a multiple of n?
Yeah, just when y is a multiple of n. Right, so it's just all multiples of n. So how do we write that? N times k such that k is an integer. All multiples of n. All right. Assume n is bigger than or equal to 2 in this example here. It's not very interesting when n is equal to 1. All right, does that include the integer 1? Is the integer 1 n?
Excluding your assumption, yes.
Right. As long as n is at least 2, 1 isn't there. So 1 is related to itself because 1 minus 1 is 0. So 1's got to have its own equivalence class. Now, when is 1 minus y multiple of n? Right? When n times k is equal to 1 minus y. Right? That is nk plus 1, the negative of it anyway, is equal to, let me see if I can do it a different way. Yeah, when y is equal to n times minus k plus 1. So 1 minus y is a multiple of n when y is equal to n times an integer plus 1. Right, so that's the equivalence class of 1. Bracket 1 is the set of all. We don't have to put minus k, it's just nk plus 1, such that k is an element of z. It's all multiples of k, and then adding 1 to them. Right, so here, this is all the multiples of n. This is all the multiples of n. This is all the multiples of n plus 1. Okay, what about 2? What about the integer 2? Is the integer 2 in this set or that set? Well, it depends what n is. Just assume for the moment that n is kind of big. N is like 5 or 6 or something like that. Would 2 be in here? In this or in this? Right, like if n was equal to 5, for example, this set would be equal to 0, well, it would be equal to, it's got to go in both directions, minus 10, minus 5, 0, 5, 10, like that. And this one would be all of those plus 1, minus 9, minus 4, 1, 6, 11. So you'll notice that 2 isn't there. So bracket 2 is going to be equal to, well, what do you think it's going to be?
NK plus 2.
NK plus 2. In other words, the equivalence class of 2 is all the integers such that when you divide by n, right, when you divide integers, right, I mean, like, if I want to do, like, 101 divided by 9 or something like that, right, it's equal to, it's equal to 11 remainder 2, right? You can think of it that way, or it's 11.2222. I mean, depending how you want to do the division, right? But you can think of it as 11 quotient 11 remainder 2. So bracket 2 is all the things such that when you divide by n, you get remainder 2. Bracket 1 is all the things such that all the integers such that when you divide by n, you get remainder 1. Bracket 0, everything with remainder 0. So what are the possible remainders when you're dividing by n? Well, 0, 1, 2, all the way up to what? What's the last remainder that you can get?
N minus 1.
N minus 1. So this is the set of all n times k plus n minus 1 such that k is in Z. And that's all the equivalence classes. Every integer is in one of these. Because when you divide by n, you're going to get a remainder from 0 to n minus 1. So for example, for like n equal to 5, no, that's not good. N equal to 4, right? Bracket 0, it's the set of all 4k, such that k is in Z. Bracket 1, it's the set of all 4k plus 1, such that k is in Z. Bracket 2, it's the set of all 4k plus 2. And bracket 3 is the set of all 4k plus 3. Right? Of course, bracket 4, right? Bracket 4 is going to be equal to what? Bracket 0, because they're related. Bracket 4 is equal to bracket 0 because 4 and 0 are related modulo n, are equivalent modulo n. Bracket 8 is also equal to bracket 0. Bracket 12 is equal to bracket 0. Bracket minus 16 is bracket 0. This is bracket 1. Is bracket 5. Bracket 9. Bracket minus 15. Bracket 6. Bracket minus 2. Etc., etc., etc. So the equivalence class of 0 is the same as the equivalence class of 4, 8, 12, minus 16. The equivalence class of 1 is the same as the equivalence class of 5, 9, or minus 15. Why? Why are these the same? By the way. Oh, it's 115. All right. Okay, so we'll talk more about this next time.